Dad?
Well, it should be obvious to even the most dim-witted individual who holds an advanced degree in hyperbolic topology that Homer Simpson has stumbled into the third dimension.
Sorry.
Here is an ordinary square. Whoa, slow down, egghead. But suppose we extend the square beyond the two dimensions of our universe along the hypothetical z-axis there. This forms a three-dimensional object known as a cube or a frinkahedron in honor of its discoverer. Hey.
Help me! Are you helping me or are you going on and on?
Oh, right, and of course within we find the doomed individual. Enough of your borax, Poindexter. Man's life at stake. We need action. Take that, you lousy dimension!
There's so much I don't know about astrophysics. I wish I read that book by that wheelchair guy.
We're going to look at 3D. We're going to look at polar and trig forms of vectors. Some of this content is a review of what we already know about two-dimensional vectors, but it extends then segues into three-dimensional vectors. So we know the notation. It'll have boldface or it'll have a tilde. The magnitude you may not know is called the modulus sometimes. Occasionally it's called the norm. I won't use that term much. Occasionally you'll see modulus, but the magnitude is written as vector v if it's a vector v with the absolute value symbols beside it. That's not new. Component form in 2 dimensions it's like that. In 3 dimensions we've seen it's like that. You can also write it in Cartesian form. Sometimes it's called a linear combination. That's an example there. So occasionally that's called a linear combination of I, J and K. It's another way of expressing that same idea. So linear combination of I, J and K. From previous work we know that I, J and K are the unit vectors in the X, Y and Z directions. This part is not new. We've recently seen that two-dimensional vectors in polar form are in the form of r theta, and the length of the vector geometrically or the magnitude is r. The other way of writing that same r for a certain vector v, we write it like that just as we saw a second ago above, and theta is the direction. It is also the angle it makes with the positive x-axis direction, positive x-axis. Three-dimensional vectors can also be expressed, and the representation is this in polar form. So you can see the r theta and then there's a phi. So we need to specify two angles. The theta has the same meaning as above, and so does the r, so they translate directly. Phi needs some explanation. We'll look at the diagram in one moment and look at that. The angle theta is the azimuth angle, the one we call the direction back up here. In 3D that same angle is called the azimuth angle because it needs to be differentiated between theta and phi. The other angle, phi, that's that Greek symbol there, is called the altitude angle. Let's have a look. In the axis system, we see vector v, with magnitude r. So there's your vector v. It's the dark purple line with the arrowhead. It has a modulus, or it has a magnitude of r. But remember that can also be expressed like that as we just saw. So in terms of r, it's easy to understand. However, what about the two angles? Well, the azimuth angle is still between the axes x and y in an anti-clockwise direction. In this diagram, This is the y-axis. The y-axis is this vertical axis that goes up to here and so on and continues in that direction, and we can see that as we curve this angle around, it moves across a flat plane. The angle Z, sorry, the direction Z, apologies, the angle theta, the azimuth angle, is once again between X and Y axes. My apologies, that's the Y axis there. This one here is the Z axis. So as usual, it's the angle in the anti-clockwise direction. The difference is that this is a plane, but there are 3 planes in a 3-dimensional system instead of just the one. So the plane that we're used to seeing when it's just X and Y, we actually have that brought up vertically in front of us. But if we lay that back down, it's lying down here, that plane. Remember, a plane is a flat rectangular surface. So that's it there. So this is why you see the X, this is the X axis here. We see a distance x2 in that direction, and this is the Y axis here. And so we see marked on here a certain Y direction. They're the components. How far is Z? Z is how far the thing climbs from the plane that I just had shaded in up to where it finishes there. That's distance Z because it's in this Z direction. You can therefore see the amount of angle, or the rotational distance, the angle that it lifts off the ground as it's such, if that's the ground, which is a very crude way of saying it, the amount that it is raised up from that plane angularly is this altitude angle. And it kind of helps remember how we use the word altitude, means lift or high or above. Formulas in front of you are not as scary as they look because you know some of them already. We've recently looked at these ones. These are a repeat and you still need to know them. We have some matching 3-dimensional ones. First of all, the easiest one to see is the difference between modulus with two components in a 3D system. It's a logical extension, and I do believe we've seen that before. The azimuth angle is found in the same way as it's found when it's called the direction in 2D. The others are different, so let's have a look. Hopefully you can see the connections between the 2D system. For X component is r times cos theta. In 3D it's r cos theta, but there's a cos phi there as well. If we had some more time on the video, I could do a lot of trigonometric steps to show you why that is the case, but due to time we'll skip that for now. You can see r sine theta exists here in Y, but there's a cos phi there as well. Z is r sine phi, not theta. There's no theta in there at all, because if you think about Z, that involves the altitude angle, and so we're not talking about the azimuth angle at all. This last one here is purely optional. As you can see, it is just a rearrangement of the one beside it. So remember, there's 2 ways of writing the same thing. R or the magnitude of vector v mean the same thing, exactly the same. And remember, it might be easier just to consider 2D an application of 3D where the altitude angle is 0. That can come in handy. Lastly, the azimuth angle, as you know, this one, this angle here, you already know that it can be anywhere between 0 and 360. However, the altitude angle is only ranges between -90 and 90. See if you can write down why that is. So in your notes, try and write down why. Make that the first thing. Call that question 1. Why is the altitude angle only defined between 90 and negative 90? And you may wish to go back to the diagram above to have a look at that. What I would like you to do is see if you can try these 2 questions here before class. If not, just show me your attempt. So I'll call that one number 2. You can see that I've pasted an answer there. You can write that in the bracket format or in the IJK linear combination format. There are your numbers. See if you can match those. And lastly, write the following vectors, or it's a vector, this one here, 12, 140, 42, in linear combination IJK form, and when you do it you should get the answer below there.